Okay, nice to see you again. Thank you for hanging around. So in the first lecture this morning, very importantly, we actually defined the Lagrangian, and then from various angles of attack, we derived the Euler-Lagrange equation. And the essential fact is, if you can write down the Lagrangian for some physical system, then you can use the Euler-Lagrange equation to tell you what the equations of motion are. And also from this you can get other insights into the behavior of the system. The formalism is very, very powerful, and there's profound truths which will be lurking there. So for example, on this slide here, I introduce, don't run, you'll trip. Take your time. Right, so I introduce on this slide one other piece of, yet another piece of jargon, I'm afraid. Then we'll be on to real concrete examples. But this is nice because it actually shows you how in this formalism you get these insights which would not otherwise be apparent. So what I want to do is just to introduce the concept of conjugate momentum, or sometimes called generalized momentum. And that means if I've got the Lagrangian, I can define this a momentum associated with the system, which I'm going to call Pk, which is dl by dq k dot. So why do I call this a momentum? Well, let's go back to the 1D case. So in the 1D case, the Lagrangian can be written as a half mx dot squared minus u of x. So we, at the very end of the first lecture this morning, we looked at this, where the u was actually the potential of a simple harmonic oscillator. But let's keep it a little more general here. Then so here we have that q1 is x, and q1 dot is x dot. So the generalized coordinate is x. So according to this definition, if I look at dl by q1 dot, which is dl by dx prime, what do I get? I get mx dot, which is indeed a momentum. Okay, so that's nice. Now this generalized momentum need not just be a simple translational momentum. It can be something else. For example, if we have a very simple pendulum, we will this Lagrangian for a simple pendulum. It's clear where that comes from, but we will actually, maybe slides a bit back to front, we'll actually be looking at this case very soon. But here's the kinetic energy, and here's the potential energy. We have a plus sign here because the gravitational potential is defined with a minus sign, so then we end up with a plus sign. But we'll come back to this in a couple of slides. Anyway, if we take dl by d theta dot in this case, then we end up with ml squared theta dot. And this looks familiar. This is angular momentum. So again, this manipulation gives you something which is a momentum-like quantity. Okay. So if we have this, then we can actually rewrite, if we wish, the Euler-Lagrange equation in a very compact and nice form, because then what's in this bracket here is the generalized momentum, and we differentiate that with respect to time. So we have that pk dot is equal to dl by dqk. Okay. And I promised you that we would get some insight from this discussion, and we're going to do that now. Imagine the case where the Lagrangian does not explicitly depend on qk. Okay, so when you write out the Lagrangian, it doesn't involve qk. So this is not the case here because this Lagrangian does involve theta. Okay, so this is not such an example, but we will see examples. In this case, then, the right-hand side would be 0. And then we deduce that pk itself is a conserved quantity. Okay, so this is very, very nice. You can just look at the Lagrangian. You can see if there's any generalized coordinates it doesn't depend on, and then from that you can immediately say, well, this quantity, this momentum quantity is conserved, and that one is, etc. Okay. And in this case, if the Lagrangian does not explicitly depend on qk, then we call qk cyclic or ignorable. So that's more jargon, I'm afraid, but I hope the last bit of jargon for a while. Okay, so that's very nice. I hope you agree. But high time, I think, that we actually plunged into a few examples to try and get some familiarity with using Euler-Lagrange and the Lagrangians. So let's start with this first case here. This is this isn't a pendulum. This is something which is sitting flat on a table. So it's a wire rotating at constant angular speed in a horizontal plane. Okay, and it has a bead on it, so this bead can slide up and down here. So what we want to do is to find the equation of motion for this system, but using the Lagrangian formalism. Okay, so let's work in polar coordinates. In polars. So then the velocity is given by r dot r hat plus r theta dot theta hat. So L is the kinetic energy minus the potential energy, but this is a very simple system. It's flat, it's horizontal. So here there's actually no potential energy, and therefore the Lagrangian is just given by the kinetic energy, and it has in principle these two components, right, the radial and the azimuthal. So it's a half m r dot squared plus a half m r squared theta dot squared, but it's going to be rotating at constant speed. So theta dot is omega, which is constant. So L is half m r dot squared plus a half m r squared omega squared. So the Lagrangian system is specified by a single generalized coordinate. So we have a single coordinate, and that is r. So this means there's just one Euler-Lagrange equation which we can write down. So let's do that. So the equation in this case is d by dt of dl by dr dot is equal to dl by dr. dl by dr dot is going to give me just mr dot, and dl by dr is going to give me mr omega squared. So differentiating this with respect to time, we end up with mr double dot equals mr omega squared. So r double dot equals r omega squared. Okay, so this is the equation of motion which we just get out in a couple of lines. So fantastic. In this problem, that's where the sort of specific Lagrangian mechanics part of it finishes. If we want to solve this equation, we have to solve it just as we have solved these equations before. So let's, we won't do this for all examples, but let's just do it for this case. So firstly, if we look at this, we see what do we end up with here. So we see this is a situation, we have a central force, just looking at this, because the right-hand side must be a force, if we now interpret it in terms of Newton's second law, which is of mr squared, n omega squared r in size. But let's look at this. How would we solve it? This is not a simple harmonic because it doesn't have a minus sign, but the solution is that r is given by a e omega t plus b e to the minus omega t, where a and b are constants. Okay? So that's the, this is a very familiar equation, so one has the exponential solutions. Let's just to take this further, let's say we have some, because these must be fixed by the boundary conditions, the initial conditions. So let's say that r at time equals 0 is, let's call that r subscript 0, and velocity at time equals 0, the radial velocity is 0, okay? Then, so putting this in, we see that R0 is A plus B. That's just putting t equals to 0 in. If we differentiate it with respect to time, I won't write down the intermediate line, but then put t equals to 0, we see that R dot equals 0 equals omega A minus B. And from this we see that A is equal to B, and A equals B equals R0 over 2. So R is equal to R0 over 2 e to the omega t plus e to the minus omega t, which if you wish you can write as R0 cosh omega t. So that's the full solution. So what actually happens, so as time goes on, it's clearly this first term which dominates. So as the thing spins round, the ball starts to move outwards with an exponentially growing rate. And that seems, that seems pretty much what you might expect. Okay, so what was happening there was that, theta dot was a constant which we called omega. Let's now allow the angular speed itself to be a free coordinate. So how would that change things? So now we get, so now omega theta not a constant. And so we end up, so we had the Lagrangian, well, we wrote this already, so half mr dot squared plus a half mr squared theta dot squared. So now we have two coordinates. So we have q1 is equal to r and q2 is equal to theta. Right? So we need to write down, apply the Euler-Lagrange equation twice. For both, okay? So so for r, then it's no different to before. We get mr double dot is equal to mr theta dot squared. So that's just what we had before, but now theta dot is not a constant. What about the theta case? Well, we have then that d by dt of dl by d theta dot is equal to dl by d theta. Now, if you actually look at the form for this Lagrangian, you see it depends on theta dot, but not on theta. Okay, so L is independent of theta, so theta is cyclic. So the conjugate momentum is conserved. So just let us, so that is what we've already agreed on, but if we just work this out brutally using Euler-Lagrange, so I have d by dt of dl by d theta dot, so that's going to give me, L is, so that's going to give me mr squared theta dot equals 0. Okay, so this is, that is this is the conjugate momentum, and it's clearly J, the angular momentum, mr squared theta dot. Okay, so that's what we learn from the theta side of things. So we can actually use this to our advantage. As we did when we were considering orbits many, many times, we can write, therefore, theta dot as J some constant divided by mr squared, and we can sub this in to the radial equation. So if we had that mr double dot is equal to mr theta dot squared. So putting this in, we see that r double dot is equal to j squared over m squared r to the cube. So we see that very, very quickly and rather elegantly, we've learned quite a bit. So this equation of motion is rather different to the one we had when theta dot was a constant. Now we see that in that case, the bead was just radially shooting off the wire. So here you see that it's damped by this 1 over r cubed thing. So the radial acceleration now drops with r, and that is because J has to be conserved. Okay, nice. I promised you we'd look at the pendulum. You have to, whatever problem you're looking at in physics, you have to come back and study the pendulum. So here we are. So let's now write down the Lagrangian for the pendulum. So we have, here we have a single coordinate we'd like to work in, which will be Q1 equals theta. And so the angular, so the kinetic energy will just be given by a half m L squared theta dot squared, okay? And there's a potential energy which is associated with the height of the bob. So U is given by minus mgl cosine theta. Okay, so that's just that. That's just the height here, and it's defined to be 0 when theta equals 90 degrees. And so L is going to be given by a half m L squared theta dot squared minus this, so I get this plus mgl cos theta. So this was the expression for the Lagrangian we actually had on the first transparency. Okay, so you should be getting the hang of things now. I need to differentiate that with respect to theta dot. And I get a ml squared theta dot. And with respect to theta, I get a minus mgl sine theta. I then differentiate that with respect to time, which is needed for the Euler-Lagrange, so I get m L squared theta double dot then equals minus mgl sine theta. Okay. So d by dt of dl by d theta dot gives that, and it is equal on the right hand side by dl by d theta. So this looks very familiar. Theta double dot equals minus g over L sine theta, which is the familiar equation of motion, but derived here using the Lagrangian approach, which I think you'll agree is very direct and effective. Okay. But you might say, well, this is greater, this is the primary thing we're interested in, but there are other things about this system which I might want to know about. In particular, what about the tension in the string? If I'm setting things up with the Newton's with forces and Newton's equations of motion, I know how to calculate the tension in the string. This newfangled foreign French approach has not managed to do that. It's just told me the theta dependence, so it can't be as good. But we can set things up in a slightly different manner, so we can find out about the tension in the string. So let's see how we do this. So this means setting the problem up such that here the Lagrangian is just dependent on a single coordinate. Let's write it so it depends on two coordinates. Okay, so we want to here add radial components, including a potential, to the Lagrangian. Okay. but we shouldn't forget that in the end, the radial length r is fixed. The r is equal to L, the length of the string. So this is a constraint. Okay, so we allow ourselves to consider what the radial part of the Lagrangian is, but we will impose at the end that the radial length is a fixed quantity, which is L, the length of the string. Okay, so let us write down the Lagrangian in this manner. So it's then we add a new kinetic term, half mr dot squared. So this allows for radial kinetic energy. And then we have the term which we just had, which is the azimuthal kinetic energy, a half mr squared theta dot squared. And then we have the gravitational potential energy, which is mgr cosine theta. And then, but we now allow for potential energy in the radial direction, okay? When this enters with a minus sign, okay? Minus VR. Okay, now I'm not going to, I won't actually specify what VR is, but having said that, let me write down what it clearly is. I mean, it's just going to be a half kr squared, right? It just will be the potential energy in a stretched spring, but we don't need to actually write that explicitly to progress with this. Right. So we now apply Euler-Lagrange again. So Euler-Lagrange. So in theta, it's going to be. So now there's going to be. So look, what we have is now two coordinates. So two Euler-Lagrange equations. Okay. So firstly, one might want to do it in theta. Theta is just going to be identical to before. So I'm not even going to write that out. It's just going to be as we had here, but instead of L, it's going to be R. Okay, so theta as before, but R instead of L, but actually R is equal to L, that's the constraint, so identical. So it really is the same as before. Okay, so what's different is we can do it for, we can do Euler-Lagrange for R. So Euler-Lagrange for R. So let's now do this. We have dl by dr dot. There's just one term in R dot, which is the first kinematic energy term. So we end up here with mr dot. We're going to need to differentiate that with respect to time. So let me write d by dt of dl by dr dot, and that's going to be mr double dot. But we also need dl by dr, and in this expression on top of the board, the second term depends on r, so that's going to give me an mr theta dot squared and we're going to get a plus mg cosine theta, and then we're going to get a minus dv by dr. Right. Now, one of the reasons we embarked on this was because I convinced you it would be interesting. Well, I don't know if I convinced you, but I said that we should at least try and find out the tension. So the tension is clearly related to the differential of this potential. I mean, the tension is equal to dv by dr. Okay, the force is equal to the derivative of the potential. Now, if you're still having energy this morning, you might look at that and you might say, hang on, one thing your tutors have told you is when you write force as the minus the grad of a potential, you should always remember that minus sign. And indeed, you should always remember a minus sign. But if you look at our diagram, you see the potential, the force here, the tension has, I mean, we know that the tension is an inward force. Well, that's the part we're interested in. And so we have drawn it with pointing in this direction, which is in the opposite direction to the r vector. So there's no minus sign here because t is defined in the minus r hat direction. So it's, you're right, your tutors are right, you should always remember the minus sign, but just because how we've drawn the tension on that diagram, there's a minus sign already in the game which gets cancelled out. Okay, so we have dl by dr is equal to I can't see the board from there. mr theta dot squared minus mg cosine theta minus the tension. Okay, and the Euler-Lagrange will tell me that m r double dot, which is the d by dt of dl by dr dot, is equal to all of this. So let me write this out yet again. Theta dot squared minus mg cosine theta minus t. So here we have a... So here is an equation of motion involving t, which is great. And just to make really clear what's happening, we now we do know, again, we impose the constraint. And what is the constraint? The constraint is that L equals R equals constant. So R double dot is equal to 0, and we get that 0, so we get 0 on the left-hand side, and so we just have these three terms. Let me put one of those terms on the left-hand side, m r squared theta dot squared, and then on the right-hand side I'm going to have a t minus mg cosine theta. So what is this here? We have, this is no more than an r squared I can write as a L squared if I wish. So this is the centripetal force, you recognise that. And what is the centripetal force? What is the force which is pulling inwards and accelerating inwards? It is equal to the tension, and then in the other direction, this is the weight which is pulling up outwards. Okay, so from this analysis we've learnt about the tension in the string, and we get an expression which you would could have written down by using Newton's second law. So that's one example of how to put a constraint in the problem and to learn more about it and be able to write down to analyse for another coordinate. There's one other elegant way to do this, and that's with Lagrange multipliers. So Lagrange is very, very relevant for this section of the course, but in principle these are all actually different innovations. He was a very bright guy. So the Lagrangian is a separate thing from the Euler-Lagrange equation, which is separate from the Lagrange multiplier method, which we will now consider. So you will see this Lagrange multiplier method actually applied in maths and in physics, even if you're not dealing with just a simple Lagrangian. But anyway, let's consider it in this case. So what the deal is here is that, so it's another way to do just what we've done here, which is to just stick with the original equation we had, but then we add onto it an additional term, which is a constraint equation, which in this case would be an equation relating R and L, and we will do that, so you'll see what I mean. But that is then multiplied by a term called lambda, and this is called the Lagrange multiplier. Okay, so this is an unknown factor. So what we then have to do is, when we write down the Euler-Lagrange equations, we have to do it also write down an Euler-Lagrange equation involving lambda. We regard this as an additional coordinate. And this should enable us to obtain the same results, and furthermore we will obtain a result for the force, because when you include a Lagrange multiplier, you can also calculate a force associated with that multiplier, which we call a force of constraint, which is given by lambda multiplied by dg by dqi. So this all looks very abstract. The best way to understand it is just to do it for this same example. Right, so I shall do so here. So this is actually the last slide. So again, we're with this pendulum, and I write down, we now have we have now this constraint equation. Which is that R minus L equals 0. Okay, so we write L as before, but with extra term. So as before, I mean L, therefore I want to write the equation as we first had it when we first started to analyse the pendulum. So just allowing for the kinetic energy term of the azimuthal term of the bob, and that potential energy, and then with this extra term. So I just need to make a comment here. So this equation is so the one on the printout, you'll also have in front the radial kinetic energy term, which we had just introduced in this discussion here. In fact, you don't need that, so I've suppressed it. What I want to be clear is that you can just write down the equation you had before for the Lagrangian, but just allowing for R now to be a variable, but then you add this guy onto the end. Okay. So let us analyze this. So we get, so now we have 3 coordinates, so that is r, theta, and this lambda. So we need an Euler-Lagrange for each of them. So I hope that now we are starting to get sufficient familiarity with this business that I can actually write down what the result of the Euler-Lagrange equation is. So for R, we therefore get m r, no, we get there's no m r, because there's just 0 will be equal to m g cosine theta plus m r squared theta dot squared plus lambda, okay? So my, just in words, I mean, I hope that's clear where that's come from, but the Lagrangian has no dependence on r dot, so that's why you've got a 0 on the left-hand side. On the right-hand side, there's just this differentiated with respect to r, so that gives this term, this gives that term, and then one must allow for this lambda r minus L, so that gives a plus lambda. So if you had written the Lagrangian with the r, the kinetic term in it, the r double dot term, that would have given you an mr double dot here. But later when we applied a constraint, we would set that to 0. So let us go straight to this. So that's one equation we now have. So for theta, what do we know? Well, for theta, we have that we must differentiate this with respect to theta dot and then with respect to time. So we have m r squared theta dot with respect to time, and that is equal to minus m g r sine theta. So let's just differentiate this. We get therefore there's a half in front here as well. I want to no, there's not a half. That's perfectly okay. So we end up with a 2m r dot theta dot plus mr squared theta double dot equals minus mgr sine theta. And then finally we must do the Euler-Lagrange equation for lambda. This is very trivial because certainly it doesn't depend on lambda dot this, so that gives me a 0 on the left hand side. On the right hand side I differentiate with respect to lambda, so I get that 0 equals r minus L, and so that r equals L, okay? So this, so now coming out of this equation, I get the constraint that I first put in. So this is the initial constraint, and it implies that also that r dot is equal to 0 and r double dot is equal to 0. Okay, so that actually means that this term will go there. So now hang on. Yes, hang on. No, what you mean? So sorry, start again. So are you talking about this line or higher up? Higher up. Okay, let me stand back so I can see it. Okay, so this is, sure you're right, I just see, so m squared m, so this was, sorry, as you might expect, my mind's moving more slowly, so I just need to think, so this is, L is, oh right, I've got it here, so I'm differentiating L with respect to R here, so this gives me a M, R, yes. You're just telling me that this should, I don't need this, right?
You made the same mistake the previous.
I made the same mistake where? Did I? Oh no. Oh man. Hang on, let me just check what in. I think everything should be okay apart from this. So I agree with this. Right. Sorry. Just check. And I had the same mistake somewhere here, did I? You should have told me there. Yeah. What, here? Just a minute. Down. No, I can't hear. Here. Yeah, because otherwise this wouldn't be, because this needs to be centripetal force. So this needs to be, this needs to be mv squared over r. Is that okay now? So, a minus sign wrong. I don't think I made any. Sorry. On this board here. What? The top board. You should have told me. Plus. Oh, hang on. Oh, just because this flipped with respect to this. Hang on. So that's the right. Is that sorted out now? I apologise, but you should have shouted earlier. That sounded like it was worth more than 2 Mars bars, but that's all I have. Hang on. Oh dear. Right. Yeah. Okay, so who put up your hands if you well, I don't know who's. Oh God. Yeah, it's got to be in order, I was told, I guess. So I'm sorry, but should have told me about the minus sign straight away. So apologies for those mistakes. But I hope we're back on track, and we're almost done here. Right. Okay, so we had the 3 Euler-Lagrange equations because we now had one for the constraint, and the last, the constraint one just gives us the constraint back. So we see that, well, the first thing is that this equation is identical to before, right? So the theta result is just as before. What's interesting is the radial equation, because now the radial equation involves what is the radial equation actually tells us actually what lambda is. That is, okay, so and I'll show you why we care about that in a second, but yeah, so here this equation can be solved to give you lambda. Okay. And that is, and it's obviously equal to minus, so let me write that radial equation and I will write it in terms of v rather than theta dot just to make it clear what we have. And the reason we care about what the actual value of lambda is because I told you, I just asserted that for a given coordinate, we have a force of constraint. So we can derive. This g, which is the g is the constraint equation. If we differentiate that with respect to r, we get the constraint force, which is given by lambda times d by dr of r minus L. Okay? So that's my constraint equation. I differentiate that with respect to r. It just gives me a trivially 1, not very interesting. So the constraint force is equal to lambda, which is equal to minus mv squared over r plus mg cosine theta, which is, again, the tension. Okay? Okay, so this Lagrange multiplier method has also given us the same results, in particular the tension in the string. So that's two ways you can get at that. Right, so I think more examples of this would be useful, particularly of using constraints. So that's what we will do tomorrow morning. And tomorrow, luckily, we only have one lecture, but let us finish there. And sorry about those mistakes.